I guess.
Are you going to NeurIPS, Devis?
No. I'm trying to keep my carbon budget low.
Yeah, no, I mean, same. I think I'm going back and forth on like whether I should go down because I'm giving some talks, but like I'm like I could go maybe just for the workshops, but then I'm flying all the way there. Like I don't know.
Yeah. Hello, everybody in the Zoom. If you want to say hi, turn on the camera and wave, it's cool. So we feel less alone with Sarah in the stream. Maybe
Okay, awesome. So it sounds like the live has started. Hey, everyone. So welcome to the Climate Change AI webinar series. My name is Sarah Beery, and I'm part of the Climate Change AI team. I serve as the biodiversity community lead for Climate Change AI. And I'm also an assistant professor at MIT in the computer science and AI lab, where my group focuses on trying to expand biodiversity monitoring to a global scale using computer vision and AI techniques. And so for those of you who are attending your first event at Climate Change AI, the Climate Change AI is an initiative that fosters impactful work at the intersection of climate change and machine learning by trying to provide education and infrastructure, community building, and advancing discourse in this impactful area. Climate Change AI conducts various initiatives to help disseminate knowledge at the intersection of climate change and AI. We offer digital resources, including foundational reports and resource wikis. We coordinate a range of different events, including summer schools, conferences, workshops, webinars, and meetups. We are actively engaged in policy conferences. We also provide grants to support the establishment of programs. We're actively involved in and engaged in policy conferences and foster discussions around AI policy in these areas. We bring together a vibrant community that stays informed of what's going on through regular updates via things like these webinars, meetups, and reading groups. And we also have a newsletter that also provides regular updates to the community. And for any more details, you can visit our website, which is climatechange.ai. And you can also connect with that wider community by joining our community platform, which gives you access to a lot of the information and resources that I just discussed, and allows you to connect with people interested in various fields of application across climate change. And then you can also read in-depth write-ups on our blog posts, which are available to everyone and cover a very wide range of topics, including research applications and presentations from the Climate Change AI team. And if you want to stay updated via the newsletter, this is an amazing resource. You can register for the newsletter and get updates on conferences, funding opportunities, research projects, new articles, and very usefully job opportunities in this space. And so the structure of this webinar is right now I'm doing this very brief introduction, and then Devis Tuia will give about a 45-minute presentation of some of his recent work. And then during this process, you'll be able to ask your questions with the Slido. And if you go to this QR code, that will provide the sort of Slido application where you can ask questions for Devis. And then you can also upvote your favorite questions. And then at the end of the sort of 45-minute presentation, we'll have an open question period where I'll be moderating questions that are upvoted on Slido. So please, without further ado, let's introduce our wonderful speaker, Devis. Devis is a good friend and actually a collaborator of mine. He finished his PhD at the University of Lausanne, where he studied kernel methods for hyperspectral satellite data. And then he traveled the world as a postdoc, first at the University of Valencia, then at CU Boulder, and then finally back at EPFL. And then in 2014, he became an assistant professor at the University of Zurich, In 2017, he went to Wageningen University in the Netherlands, where he was chair of the Geoinformation Science and Remote Sensing Laboratory. And since September 2020, he's actually been back at EPFL, where he leads the Environmental, Computational Science, and Earth Observation Laboratory in Sion. And there he studies the Earth from above with machine learning and computer vision. And today he'll be giving a talk about recent work where they use remote sensing to enable monitoring of life, both above and underwater. So take it away, Devis. Thank you so much.
Thank you very much, Sarah. Thank you, Arthur, and thanks everybody for being here. Let's see if is the screen showing correctly.
Looks great.
Yeah. Fantastic. So it's great to be here. It's great to see you all. I should see it too. Almost see you all. And today I wanted to talk a little bit about our recent works in water remote sensing, actually, which is something relatively new in my laboratory. And in a way, it's kind of a discussion of recent works and new things that I'm passionate about, that a little bit different from my usual unused uncover mapping problems. And I hope I'll be able to share my passion with all of you, and we will have a good discussion, and who knows, maybe some collaborations in the future. All right. So the idea is to talk about water, which is kind of a very complex medium and set of ecosystems, and I by no means want to really cover the whole complexity of life below water. And so I decided to focus on some of these sub SDGs, which have to do with basically two big groups of research topics. One being the reduction of marine pollution, and that's going to be one part of it. And then we're going to talk mostly about corals, basically, and how to protect and, in the long run, maybe also restore those ecosystems. Why? Maybe some of you are asking yourself this, and there is a variety of reasons. I think that probably the first reason that I can think of why we want to protect the oceans is because they are definitely a major source of food for the humankind and also for many other animals. And so seafood and fish are a great source of proteins. And so it's key to have healthy oceans that are not polluted, for example, by plastics that then decompose into microplastics and enter the food chain. And we really don't want to have these microplastics in our systems. Otherwise, oceans, and more especially coral reefs, are full of life, and I hope everybody is aware of that. And even though coral reefs cover a tiny little part of the oceans, it actually hosts a very big part of all the marine life that you find in these many oceans. So if corals don't do well, we lose very important ecosystems. Okay, and it's not only about fish, but it's also about all these other ecosystem services that oceans give to us. That can be that coral reefs protect coastlines because they break the waves, for example, and they are beautiful, so they are an economic driver for tourism. So there is a bunch of reasons why we want to care about coral ecosystems or all kind of coastal ecosystems. And despite of all these nice things, if we look at what is going on in practice, things are probably not doing so well. So if we look at the corals of the world, we can say that in 50 years, give or take, we have lost half of them. And pictures as those that you can see on the left, so a coral reef that is completely bleached and dead, are more common. If you are divers, maybe you have witnessed that yourself. Is not a pretty sight, and actually makes me very, very sad. And on the other side, not only corals are suffering, but also oceans have more and more plastic pollutions. We sometimes see that when we go on holidays, for example, but there is also this gigantic plastic patch that float in the oceans, and the size is something that gives me the I don't know how to say this, but it's a lot. Okay, so the basic question is which feature do we want to have? Now, do we want the one on the left or the one on the right? Knowing that, believe it or not, these two pictures have been taken on two sites that are a few hundred meters apart from each other. So it's really something that is localized, that it goes very quickly, and it, in my opinion, require all our attention. So in order to look for an answer to this major question, I want to talk about two things. The first is something that happens above the water, and the second one will happen below the water. And this is basically the structure of the talk. We will have two parts. I'll try to keep them to 20 minutes each. I guess you have also other things to do than listen to me on a Wednesday. Okay, cool. So let's start with the above water part, where we're going to talk mostly about how to detect marine litter from space, because a situation like the one you see on the left actually is not so uncommon, especially when you are close to major rivers, deltas, or this type of places. So looking at microplastics is a big problem, actually, because all these plastics, as I said in the beginning, tend to decompose into microplastics. So, and when they decompose into microplastic, they become very difficult to catch. And when they are difficult to touch, they basically enter the food chain, and they have been found in a number of animals all over the globe. So as far as Antarctica, or also in our own stool, for example. So it means that this plastic is around, and it's not because we don't see it that we don't ingest it, and it doesn't bring problems to us. And this has huge impact on our health. And so I guess we all can understand that we don't want this to happen into our stomachs. But despite of this, the amount of plastic is insane. If you look at the statistics on the left, you see that the quantity of plastics is very big. So we're talking about more than 150 million tons, but 10% of it keeps getting added every year to the oceans in a growth that is actually exponential. So if you look to this graphic to the right, you can see that the growth is indeed exponential. This is the black curve. It's going up, 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 up. And as of today, as of a couple of years ago, the vast majority of it is basically discarded. Okay, it's discarded. It ends up, a good share of it ends up in the oceans, unfortunately, not all of it, of course. But the thing that we need to achieve is actually what we see here in these projections. I hope you can see my mouse, where what you want is to have an exponential increase of recycling and incineration. So this is happening on the side of what I'm talking today. The thing that we observe is that if things go as planned, the trend will become linear, but still a lot of plastics will enter the seas. And this plastic is what we are concerned with, as what we want to catch. So there is a bunch of people working on how to collect this plastic as fast as possible, let it be directly into river deltas or when it gets into the oceans, by having all kind of campaigns to collect this. But it remains at a scale that it's not global scale. People do what they can, but the story is that even if it's at a small scale, the amount of plastic that is collected is very, very big. So in 2018, there was this exercise in the Bay of Biscay, where in a little bit more than 2 months, 16 tons of plastics were collected. This is a lot. And why can we collect this so efficiently? Because thanks to the ocean currents, the plastic tend to aggregate in what we call windrows. Okay, and windrows are these big aggregates that actually are visible, that allow people to actually go and collect where we can. And for us, it's a big advantage, because if the aggregate is big enough, we start to see it from above, so from satellites or from aerial sensors. Okay, and this is basically the story of the study that I want to present now. Is to see if having this satellite data that are collected already for other scopes, maybe, if you use this satellite data, we become able to detect the plastic and then empower people who make the collection, typically companies like the Ocean Cleanup or the Sea Cleaners, who have as a mission to go out with boats and collect the plastic. Okay, the question is, how well can we do it? Which type of models are we able to develop to detect where the plastic is, then map it, and potentially monitor it if we look at a large temporal scale. So I don't know how many of you here in the room are remote sensing persons. So let me just give you a 2 seconds crash course of remote sensing. So the two sensors that we were looking at are called Sentinel-2 and Planescope Devis. So they're very different. Sentinel-2 is like a big satellite constructed by a consortium led by the European Commission. And the mission of Sentinel is to provide free data to whoever needs it. Okay, so it's free data that you can download yourself. It's quite coarsely resolved, so we're talking about 10 meters per pixel, and the satellite comes back to the same place on its orbit every 2 to 5 days. Okay, more 5 to be honest. And then we have this image on a revisit time that it's a little bit low for what we want to do, but okay, we have the whole planet, we have it at a resolution that it's decent. So I think that's a great type of data to work with. On the other side, we have Planescope, and this we are talking about a constellation of very small satellites, and it's the satellite that's built and operated by a company, so they're not for free, and they give you a much higher spatial resolution, or roughly 3 meters, and possibly every day. So depending on clouds, depending on a number of things, maybe you don't have them every day, but that's what is technically possible, let's say. So if you look at an image taken by Sentinel here on the left, you can see more or less the scale of the problem you're able to observe. And if you look at the same square as here, the red square, I'm showing you the same image acquired by the planet data, and you can see that the amount of spatial detail, extra spatial detail that you can get. So of course, everybody would like to work with the planet data in a way, but then there are like economical reasons and also spectral reasons, that because the planet data are red, green, blue, and infrared, while the Sentinel gives you a full spectral range of signal. And this is kind of important because if you have only the red, the green, and blue images, so if you look only at photographic images like the one of your mobile phone, well, you can't see the plastic very well. So here it's a scene with actually a lot of plastic, and you can just see this part that is really out of the water, and the part that is submerged is very difficult to see. Well, if you use the infrared signal, for example, you can extract indices that help you using the infrared signal to see a little bit more of where the plastic is. All right, but even if we use these different indices, we realize that the problem is very complicated. Like if we compare the NDVI and the FDI, which are two different indices relying on the infrared, we can see that the plastic occupies a certain part of the indices space, but it's still a very mixed business. And it's a mixed business where we can see a good share of the plastic, but there is also a lot of confusion. For example, we can get confusion with respect to the coastline. Okay, you could say this is easy. We know where the coastline is, we can remove it. But then clouds, for example, clouds are quite our enemy, or other objects that we are not very interested in, like the ships, for example. These are floating objects technically, but they're not the floating objects that we are interested in. So in a way, we need methodologies that are a little bit more advanced to be able to then have the right detection of floating objects that we can give to those companies who do the plastic connection. Okay, so the idea of this study was to build up a deep learning model that's starting from a set of images from Sentinel-2, so the 10-meter images, and the indices that you can extract from them will then lead us to a Devis probability map, which is basically a probability that we are observing a debris in the sea. Okay, the model it's quite classical, so you can imagine this is a semantic segmentation task, so it's something based on UNet. You can have several different tastes of it. In this specific study that was led by Mark, we compare the UNet and the UNet++ as two different architectures. You can use your own. It doesn't really matter. We will see in a second the performance do not really change incredibly. And you can get the preprint on the archive link you can see at the bottom in case you're interested. And basically, what we did, beside of choosing one semantic segmentation architecture among the 500 that exist. Well, we thought of really focusing on the data set. Okay, we really started for the principle that it was very important to put the accent on the data. And so we first collected with some colleagues what we call the floating object data set, which is a collection of images where we know there are debris because they were mentioned in social media article, and starting from the social media article, we got the location went to image, and then we did manual detection of the debris on the images at very high resolution. And then we also used a second data set called Marida, which was collected by some colleagues in Greece, where they were more interested by types of plastic, but still we could binarize their labels and then have a semantic segmentation set of labels about plastic versus non-plastic. Okay, so the annotation looks a little bit like that. So this is from the floating object data set, and it's really, you know, manual annotation done very much zooming in as much as we can and relying on expert knowledge to have something very precise about the plastic debris. And not only we were after the annotation of the plastic debris itself, but we also collected a set of data sets telling something about the object we didn't like, such as the ships, for example, because the ships are something we really don't want to get in our detections because they are not plastic. I mean, they are in a way, they must have some plastic, but that's not what we are interested in. And so we got this data set focusing on ship, and we use that as negative samples. So if in a place there were some ships, we will give them to the model with a ground truth of 0, so that the model learns that what is a ship is not to be detected. So how did that work? Well, there is a bunch of tables. You can look at them in the paper in detail, but in the end, so we observed a number of things. And the first is probably stating the obvious, so that the deep learning model that has access to spatial information and everything you want tends to perform better than the random forest. Fair enough. But I mean, if you look closely enough in Durban, for example, this is not the case. So, you know, it's not always the deep learning models winning every time. But okay, on average, let's say that the deep learning model is doing very good. And the second thing that I think is much more interesting, actually, is that the type of data you use matter a lot. And this also sounds like stating the obvious, but, you know, people have been obsessing on methods for long enough. And I think it's also time to give the data a little bit of credit. So, you know, when you work on the original data, you can get to a certain performance, but when you start collecting different data and you care about your negatives and you really do like a data-centered type of approach before you even start training whatever model you're using, actually you reach much higher performance in all the cases. So I think it's important to look at the two aspects at the same time, the data and the models, and then you get to the best of both worlds. Here are a couple of visualizations. You can see more in the link below if you want. I guess the slides will be shared afterwards, so I mean you don't have to write it down. And then I mean you can see that, for example, in this column here, we're using the enhanced data set, and our detection become much more precise. And this is basically what I'm trying to get at, is that not only the model is important, but the data as well. The funny thing is that when you have a model working for Sentinel at a certain spatial resolution, then you can tune it to other sensor or other resolutions. And in that case, we're kind of lucky because Planescope is a kind of a sub-spectral resolution of Sentinel. So we can reuse some of the weights and just tune it lightly. And the funny thing is that we are then able to detect this plastic target that were deployed by the Plastic Leader project, some colleagues in Greece in 2022. And we could detect the different panels across time. And this was kind of a good result to see that not only we were detecting on a certain sensor, but we were also able to work cross-sensor and across time, therefore having a kind of a monitoring capability that I found was pretty neat. Okay, how well am I doing with time? Sarah, I don't have time on me. I don't know.
You're doing quite well. It's like 11:25, so you have
super.
So, 20 minutes?
So I'm halfway through. So so I'm happy because not having a watch is a little bit disturbing, but you know, life. Very good. So now we have been looking at one possible application of remote sensing, looking at the water surface from space in this case. And I invite you to actually jump in the water now. And we're going to go and see a little bit closer to coral reefs and to see ways how we can monitor them with low-cost remote sensing systems. Okay, and this is some research that we have started roughly 2 years ago, and I'm super excited about it. First, because I'm a very passionate diver, and secondly, because it's very new for me, and I really like it. Anyway, so first things first, big credits to Guilhem Bangprandi, who takes all these beautiful pictures, because he's our science leader for the marine biology part. And I mean, all these beautiful pictures you will see are taken by him, like this one. But apart from the credits, so let's talk about coral. At the beginning, we have talked about the importance of corals as protectors of our coastlines, and also as the kind of the house and the restaurant of a lot of fishes, like a majority of fishes in the oceans. But as you remember, unfortunately, due to the increase of temperature in the water and all kind of anthropogenic stress based on pollutions or over tourism, you name it, well, corals are unfortunately not doing so well, and we have lost roughly half of them. But there are some places for example, in the Red Sea, where the corals still resist much better than anywhere else. So the Red Sea is one of such places where it has been discovered a few years ago that the corals there have a heat resistance that is very, very unexpected. They can resist temperature of +3-4 degrees without bleaching, which is something that other corals, for example, in the Great Barrier Reef, cannot sustain. And so we kind of started this adventure with a team of marine biologists and of geneticists to try to understand why. There is a bunch of theories, and still I don't think anyone has the final answer. One of these theories is that this is due to history of the corals, because if you look at the map of the temperature of the water of the Red Sea, you can see that in the southern part, close to Eritrea and Djibouti, the water temperature is much higher. And long time ago, millions of years ago, the Red Sea was a kind of a pond. It was disconnected from the ocean because of some how you call that? Well, it was disconnected from the sea because everything went higher, and so everything that was in the Red Sea died. But after some time, this phenomenon was finished, and then the Red Sea was reconnected to the ocean by the southern entrance. So it was the only income of salt water in the Red Sea, and so the corals started to recolonize from the south. And by recolonizing from the south, they had to kind of cross all this very warm part before being able to recolonize the northern part. And because of this transition, they were forced to develop this resistance to temperatures. They were much higher of what they were supposed to resist in their natural habitat. So this is one theory. And this is the theory that we are trying to prove by observing, mapping and monitoring these corals, taking samples, analyze them in the lab, and so on and so forth. So our part is obviously the remote sensing part, so the map and monitoring part. And of course, we're not the first person in the world that have started to do some kind of mapping of underwater footage. But if you look at the literature of like important papers, like cornerstone papers in the field, you can also see that it's not an easy business, because the digital imaging era is not so old, and also the technology that comes with is still under development. So if you look at this paper here, for example, we see that we have a set of digital images that are taken on a reef that is 28 meters per times 6, so it's not very big, okay? And then there is a lot of processing made by proprietary software. In this case, is Photoscan, which is one of the reference softwares in the field, which takes roughly an hour to have the small 3D models. And then there is roughly 20 hours of manual work to extract the information about the reef. Okay, so we're talking about a 30 meters long reef, and it's almost 1 day of processing. Okay, and we haven't started analyzing it. I mean, this is basically just creating the 3D model. On the other end of the spectrum, if you allow me the joke, there are people who are deploying sensors that have a very strong spectral range, which is called hyperspectral sensors, and they can really scan at a very fine-grained level the spectral properties of coral. So imagine that it's a camera that it's not just looking at red, green, and blue, but it has like 200 spectral bands. And that can allow you to see in the visible range, in the infrared, in the shortwave, maybe even in the thermal. So every coral bit that you look at with this camera gets a full spectral curve or their optical behavior. And with all this information in this paper, they've shown that it's possible to actually characterize the species of the coral at a very, very fine-grained level. This is fantastic. And this is another cornerstone paper. But at the same time, you need a camera that has a certain price. So it's not something that, you know, everybody can have in his pocket. And so to scale this up to actually continental monitor, this seems a little bit complicated. It's good for other things. So in our case, we thought to take a kind of a middle way to make some setup that was, in a way, affordable, economically speaking, and scalable. So it's something that we want to be able to export to many other reefs, and something that is easy to acquire and to replace, because things break, unfortunately. And then it's also something that we hope will allow us to train local communities and like empower the people who want to protect their own reef to make their own monitoring and having the tools to do this themselves, instead of us being, everybody being captive of us going there and taking the images and so on. So we started with this adventure, and okay, we started a completely new business. So we started by buying some cameras and let's give it a try. Let's see what happens. And, you know, we made a little bit of road in these 2 years. And you can see here Jonathan Sauder in the picture. So he's a grad student in my team who is actually the lucky one who goes diving to all these fancy places to acquire the data. And basically we have a system that grows with every time we go for a fieldwork campaign. And now we have a system with 6 cameras looking at different sides of the reef, so we can cover more ground. But basically, in the end, this setup allows us to acquire enough data to train deep learning models that will replace this slow 3D model production chain that I was talking before. And this basically this deep learning setup, you can see it here in this graphics, where basically you can see that it has 2 different objectives, 2 different tasks that both rely on the video acquired with the GoPro. Okay, so it's really only the GoPro. We don't have anything else. Okay, we don't have lidars, we don't have stereo setups, very complicated things. Okay, if you go on holiday and you have a GoPro, you can do it. And basically this tries to solve 2 tasks, one being the semantic segmentation of the point cloud. So this is a supervised task. Yeah? So we need someone here like Gabi with labeling some corals for us. So we need human intervention to know which classes we are looking for. And the second stream, it's more about predicting depth and pose, which means having a depth estimation problem solved in order to make the 3D model. And these 2 parts work together, and we will see in a second how, in order to reconstruct a complete 3D model of the reef with semantic information. Okay? And the thing that we really want to achieve is that once trained, this model needs to 3D reconstruct in plain video time. Okay? So if you are diving and your video takes 5 minutes, it needs to take 5 minutes max to give you the 3D reconstruction of the reef. Okay? So we tested already in 3 places, in Israel, in Jordan, and Djibouti in 2022. And in 2.5 weeks, we go back to Djibouti and we try the new system in the water. So to be continued. So we have said that there are 2 different parts. So the first one is the 3D one. Okay. So basically what we do is that we have a single camera here, because we want to have a setup that anybody can use with a single camera. So we do monocular depth estimation, okay? So we use the fact that we have a video. In the video, we have frames, a high rate of frames that we can use kind of to simulate the two cameras. So we have one video for which we predict the depth with an encoder and decoder system. And at the same time, we predict the pose, which is the position of the camera. And then we do the same thing for the next frame, right? And we get two depth prediction and a pose estimation for the second. And then we project one depth map into the other and the other way around. And we have losses to backpropagate in a self-supervised way. Okay, so by doing so, we simulate that we have a second camera. So like we have the left eye and we simulate having the right one and the other way around. And by doing so, we're able to learn a model that does depth prediction in an unsupervised way. So we don't just use one frame at a time, or we give some temporal context by having one encoder that encodes a 7-frame sequence into an encoding, and this gets summed. This goes straight into the pose estimation network and also gets summed to the single image encoding to the depth estimation network, so that we don't leave every image on its own, but we also give a little bit of context of what is happening before and after. And after training, it looks pretty neat. So I just show you this video where you can basically see one of the videos we acquired. I think here we were in Israel, if I remember well. And you can see the depth map below, where everything that is blue is close by and everything that is red is far away, basically. And this is done in video time. So of course, we don't do it hardware on the GoPro while we're diving. We don't have access yet to the GoPro, but we do it on our computers. But at least it doesn't take multiple hours for a reef that is, in this case, a little bit more than 100 meters long. This is pretty cool. The second part of the system is the semantic segmentation part. And this is something, it's a classic computer vision application. So I imagine that we have all these frames. And so we take the videos frame by frame. And for some of these, we have hired lucky students, hired students to make the ground truth that we can see here. And basically, I mean, this have been annotated to the best of the knowledge of the annotators. And then the model is basically making the prediction for these classes. So these are the classes we have at the moment, and every frame in the video gets annotated by this semantic segmentation network, which is based on a ResNext backbone. If you want to know the accuracy for Jordan and Israeli, that all the details you can find in the preprint of the paper down here, it's more or less 85% accurate. It's not perfect, but it's good enough for what we need to do. Because we need these semantic segmentation maps for two things mostly. But the first is to see which type of corals are there. I'll come back to that in a second. And the second is to detect and map things that are not supposed to be there. Okay, like for example, the line that we are following while diving. So it's this green light here that you can see. This green line here is just a rope that we put in the water to be sure to always swim the same part of the reef. Another thing we're not interested in, and just move to the next slide, is fishes. It's not because they are not interested. It's just that we don't need them to 3D reconstruct the reef. The fish is not part of the reef. And the third thing is divers. So you can see here, for example, Guilhem in the water. We don't want Guilhem to become part of the 3D model. We want him to be removed, actually, because that's a transient attribute of the video. And because if you don't, then your 3D reconstruction looks like this one at the top, where the model is trying to take the pixels of the human and put them in the coral reef, and that's both disturbing and wrong. But what you need to do is basically to classify every pixel of the frame. And when a pixel is classified as a human, the corresponding point in the 3D model is just discarded, because that point you will see it from another frame of the video. So you will be able to fill up that voxel in another time from another time of the video. So basically for us, it's a way to remove all unwanted parts of the video. And finally, I mean, the thing looks pretty amazing. So you see here, it's it's basically the video here on the top left. So you are actually diving. If you're not a diver, that's your first dive. And the system is producing the two outputs, one being the depth map that you see at the bottom. So blue is close, red is far. And here on the right, you see the semantic segmentation map that, of course, it blinks a little bit because it's doing that frame by frame. So we could do better by encoding some temporal consistency, but we have an idea of what's going on in the video and the type of corals we are observing. Here at the bottom right, you see the 3D model being built one frame at a time. So for every frame, all the pixels classified as reef classes get projected in the 3D model, and you see it here. If I advance a little bit the video, hop, you will see. So the 3D model gets more and more larger and larger, one frame at a time, and you have then at the bottom the same 3D model, but this time colored not by the colors of the video, but by the results of the semantic segmentation model. And all this is done in video time. So the video is running and the rest is being predicted. And the results you can have, then you have this type of 3D reconstruction that you can move around, you can zoom them in, zoom them out, and you can then do all kind of morphometric analysis of the coral properties, and not only morphometric analysis, but you can then also start looking at which type of corals are bleached, which one are dead, which are not healthy, and then extract all kinds of statistics that allow you to characterize the reef and then make some monitoring. If you repeat the measuring in time, you can have this type of graphic where you can see the composition of the reef, and you can compare different places, and so on and so forth. And this is basically the data we want to work with afterwards when we collaborate with our marine biologist friend and our geneticists, who will have taken samples, and we will try to make connections between the morphology and the genetics, and hopefully trying to understand this mystery of the Red Sea, and who knows, maybe holds the key to save the coral reefs everywhere else. All right. I hope you liked the tour. It was it's a new thing to me to present, so I maybe not so smooth as usual, but I hope you noticed the passion and the envy I had to show you these results, which are very fresh. You see the papers are preprints, so everything is new, and I think that working on oceans is both cool and important. And I hope you think that too, at least after this talk, or even before. Maybe you're excited to work on this. Please reach out. It's very fun. You visit awesome places as well. This is not to be minimized, and it forces you to work in an interdisciplinary way. I think I have never learned as much as since I was working with this team of wonderful people who are know things that I would have never expected about the underwater realm. And also a big shout out to the Transnational Red Sea Center of EPFL that makes all this possible. They finance us and rent boats and make us do the fun parts of the research, and also research institutions like the Swiss Data Science Center and companies like the Ocean Cleanup, who are actually out there getting the plastic that we detect, and trying to make the extra mile after deep learning into something really useful. So thank you very much, everybody. And I'm here for questions. Please don't hesitate.
Thank you so much, Devis, for an awesome talk. And I don't know what you're talking about. I think that was a really great and comprehensive discussion of some of your recent work. So
thanks.
Not any more clunky than normal. So there are a couple of questions on the Slido, and just a reminder to everyone, if you want to sort of ask questions or upvote, you can do that on the Slido. So the first question from the audience is asking about the marine debris project, and specifically, what are the next steps after detecting the marine debris? And you mentioned the Ocean Cleanup as like one possible organization, but are there other specific agencies that you sort of contact and work with? Like, how complicated is the process from that AI model result to actual impact?
That's a very good question. And it's a question that and it's difficult to answer because, of course, when we look at the remote sensing side of things, we have one image, we get some labels, we get some maps. They're good, we're happy, but it will be really not okay to stop there, because the ocean cleanup, they cannot rely on those maps to go and collect the plastic, because the moment we tell them the plastic is there, they maybe take 3 hours to get there, maybe the plastic is somewhere else. Because the ocean is a dynamic environment, and you need to be able to follow the ocean currents. So now we are working on extensions where we track actually the debris that we detect using tracking models that do not depend on satellite imaging this time. And we try to see how to help these companies to actually get to the right place. And then it's all kind of probabilistic, prediction of where the plastic is going to be. It's super high uncertainty. So it's a complicated project that we just started. It literally started this month. So Emanuele, that you can see here in the picture, he's the boss there, and also Mark. So this is the plastic team, let's say. And we're trying to make that work with the ocean cleanup. So they are partners in the project. And then there is a lot of interest on the satellite side by the European Space Agency, which is really interested in looking into better ways to detect and monitoring the plastic. Will there get to some kind of, EU policy level? I hope so. For the moment, we're not there yet.
Yeah, no, that's fantastic, though. So, okay. Now the next question from the audience is about that second project, and it's specifically asking how these different environmental factors underwater, such as, changes in lighting, the turbidity of the water, things like marine snow, depending on sort of where you are in the water column, how does that impact your underwater models? Possibly things like, you have a really good semantic segmentation of people and fish, but are there other things in the water that you might not be as good at segmenting that could actually affect the accuracy of that 3D reconstruction?
These are all excellent points. What can I say? This is our first attempt to do this, and we've started by doing what we know. So using these semantic segmentation models that we trained with labels given us first by ESPER, then by our students that we trained. Everything is perfectible in the sense that then the influence of water turbidity, for example, is something that we didn't study so far, because we're lucky of working in an environment where the water is super pristine. It's true that in the Red Sea, the water is super pristine. So it's a problem that we didn't have so far because we were working there. But it's definitely a problem that is extremely important to make this scale across the continents and the different oceans, because visibility is not always that good by far. So yeah, I would say is food for thought for the future. Then depending on the classes, we have set up that set of classes that is something that a human, an expert, could detect by using the video only. As you if I can go back, I'm still sharing the screen, right? So if you look back at our class set, we're not going down to the species level, because it is something that we cannot discriminate using the video data only. We will need either some hyperspectral data like the one of this paper of 2022 I showed before, or some genetic analysis of the different coral parts. This will be the way to really discriminate the different species. So we keep it as a very coarse level with 2-3 classes that are easy to visually discriminate, and some ELF stages: alive, bleached, and dead. And we are very well aware that when we move to another continent, the same type of coral will look very different. So I think that there is a lot of domain adaptation to be looked at in all this, and life is long.
Okay, so actually, I guess that does kind of lead to the next question from the audience, which is, from your perspective, what are the hardest problems to overcome in this domain, both from a research perspective and from a practical perspective?
So from a research perspective, I guess all this gigantic variability of of the object we are observing in different places in the world is the one to overcome, which is something I'm sure you observe as well in the camera traps works. Like the main shift problem is something that will always be there when we look at data set in the real world. And so that's definitely on the research side, one of the big ones. The second thing is that, connecting to the previous question, is that we are underwater. So it's a medium that has an impact on the videos that is very different from air. In air, we're maybe used to the effect of fog that makes all your images less contrasted, you name it. But here we have reflections from the surface. We have water turbidity, we have particles, we have a lot of distractors, the fishes and so on. So being able to deal with those is something that I think will be not impossible, but will need some brain power. Like you can imagine of running your nerve on this and doing a 3D reconstruction, but there is a number of things that do not happen out of the water that you need to be able to discount for. So in the research side, I think this is quite central. On the practical side, I can share our experience in the region of the Red Sea. I mean, we work with, let's try not to make it political because it's not the right moment to talk about those things. But, it's protecting this. It's something that is really federating. So we're talking and able to talk with countries that sometimes don't talk to each other, but there is also a lot of difficulties in making everybody work together for the same goal. So I think that the implementation part of the every policy that will be for the well-being of corals will have to go through a lot of discussion and consensus and regulations that are completely out of our hands. But this will impact where you can go, what you can measure, and which type of actions you can implement. So I think that the real difficulty for this is like putting everybody on the same table. Yeah,
and it really kind of gets at, I was recently at a talk where someone was saying that a lot of the problems we have with AI systems are really human problems. And I think in terms of the deployment of AI systems, that's also true. It becomes a system that you can no longer control. It becomes very messy and very human.
Absolutely. And I think the fact that trying to empower people with the technology it's a good way to go, at least in my opinion, because we're not like parachuting technology there, but we're trying to train them so they can really run it themselves and seeing the pros and cons, and we're trying to really build something down there where people are owners of this technology rather than calling us whenever they need us.
Yeah, awesome. So so there was actually another maybe two questions from the audience that I'm going to make the executive decision to sort of merge. And they were kind of both around this discussion of like alternative ways to try to think about monitoring corals. So one brought up the feasibility of actually monitoring coral bleaching from satellites. In what cases and to what extent can you actually use satellite imagery, stuff way above the earth, to actually understand the coral, understand the ocean? Yes. And then another question was kind of talking about, you talked about potentially incorporating hyperspectral, but they're, especially in areas like I work some in the Arctic, and there the water is often has a lot of glacial till and you can't see through it at all. In areas like this, when should we think about alternative modalities for monitoring the ocean, stuff that's less affected by some of these water things like sonar or bioacoustic sensing? Yeah. So I guess I'd love to hear your thoughts on what are the complementarity of these different modalities.
There are actions trying to map bleaching from space. For example, the Allen Coral Atlas did a kind of a cartography of the state of the corals worldwide, which is at a scale that you can only do on satellite or with a massive crowdsourcing exercise. You have data when the reefs are very shallow. The moment it gets deeper than a few meters, I don't make me say a number. I don't know. It really depends on the transparency of the water column, but at some point you just don't see the reef anymore. So in those cases, I think, unfortunately, the satellite image becomes not so useful. It's something that we looked at a little bit with the students as well. And there is also a number of other things that come into play, like, the wave pattern, the sun gleams. There is a lot of things that makes that you just don't see what's going on through the water. So I think it's a great effort if you think about the scale, but you need to be kept with reason, because there is a number of situations where it's just not possible because of the sensor data that you get. Regarding sonar and acoustics, I think it's fantastic new sources of data, but they apply to different problems. Like for the acoustics, I guess fish monitoring is something that you can do because you can know where they are because you hear where they eat. But to map corals, I'm not sure. But I'm really not an expert, so I prefer not to take risks here.
Do you see, have you thought at all about sort of multimodal monitoring, particularly in these areas where you're doing this like very comprehensive repeat evaluation and looking at change? Do you think there's potentially value in incorporating some other monitoring modalities?
If you're interested, like in fish population monitoring, that's definitely something you should look at by videos and sound, for example. I guess your system will become more accurate. There was this talk by Kakani in CV for Animals at CVPR, where they built this massive multimodal system for very deep water imaging and video, and they had so many cameras. Some were thermal, some lidars, and they were trying to use everything at the same time. I guess especially in such a harsh environment where basically, everything is trying to kill you, first pressure and then everything else. I mean, you try to get all the data that you can with different sensors. And yeah, I mean, you need a source of light because it's completely dark. And I guess here we're talking about an ecosystem that is easily reachable humanly with low risk and which can be scaled by very consumer grade cameras. But if you start to go much deeper, you cannot use something like that.
Yeah, it's interesting. It really kind of comes back to this question of resource allocation. And in this case, because it's a human can just swim there from shore, you don't need to think about like the resource allocation of access becomes a lot less of a factor. Absolutely. And then you can scale much more effectively if your sensors are as cheap and as efficient as possible. So that's quite interesting. So actually sort of maybe along those lines as well, like with that 3D reconstruction that you guys have been doing, do you actually sort of know the depth of the transects at which the videos are taken? Like, do you have a way to actually understand the depth of the sensors? And also, do you actually use sort of optical flow or different types of motion in that reconstruction? Is there kind of a temporal dimension, or is it really done predictively frame by frame?
So it is done predictively frame by frame, but we have this plus minus frame that kicks in for context. It's not optical flow directly, but it serves a similar purpose, I will say, that you want to kind of keep going in the same direction. You know that the pose of the camera will not change abruptly, but also because we know that we have been swimming in a certain way. Now, the only thing that we know is the entry point and the exit point, because we have some GPS there. And this is why we have the line, is because when we are underwater, we don't have GPS signal. So yeah, I mean, the exact depth is maybe a little bit of a stretch, but we can reallocate the camera pose with respect to the entry and the exit points. That's the best we can do for now.
And then sort of what frequency are you collecting the data, and what frequency do you sort of think is maybe necessary or sufficient to monitor the evolution of those reefs over time?
So we are not collecting at a very high frequency. Like we can go maybe twice a year, and we want to cover the whole of the Red Sea if possible, if geopolitical situations allow. But the story is that wherever we go, we work with locals, and we make a workshop. We train local students. We give them hardware, and then they will keep taking the data. And so we try to create some local little data centers where people who care about their own reef will then go and do the monitoring more often. I don't think you need to go every week, honestly, unless there are some specific events. But even more important is to have someone on site. If something particular happens, you are able to jump immediately in the water. I mean, if it's safe, of course.
Is that data sort of, do you have a sense of that it should maybe be centralized at all, or is it really just a distributed network where each individual actor is collecting data of their part of the reef? And at what point does knowledge get shared?
I mean, it's a work in development. We've been at it for 2 years. So, I mean, the point on the horizon where we want to be will be to have a distributed system and just basically moving around the results. That would be the perfect thing. But I don't know. I mean, to be honest, we haven't really talked about that part very much. Also because we have been in 3 places so far, and. Yeah, and the monitoring part, we are really implementing it only in Israel because that's where we have been more often because of collaborations. And yeah, so this time we're going for a second time in Djibouti in 2 weeks. So that's going to be like the first time we really do revisiting monitoring in time, not in Israel. Yeah, so we'll see.
Very, very cool. So what other use cases do you think are maybe like the most promising for above water sensing of the ocean, and also maybe for below water sensing, like maybe even using the exact same system that you've currently developed? Do you see sort of other clear, impactful applications?
Well, above oceans, there is a lot of scientific applications that are of great interest to understand the effects of climate change. So everything that has to do with water currents, with water surface temperature, and these type of things. We have tackled the plastic problem because we were interested in it first, and also because it's something very visual. So it's something that we could detect from space and create our ground truths and so on. But there is a whole community out there doing oceanic modeling that maybe wants to start this discussion to see how we can hybridize models and get to new ways of running ocean current models that will be faster, emulators that can allow more scenarios, calculations in a reduced time. I don't know. I think there is everything to be gained in science. Then in terms of products, I don't know. I mean, monitoring animals, I'm not sure at large because they tend to dive. So at some point you don't see them anymore. But I don't know. In science, I see it, but for business cases, I've thought less about it.
Yeah. Awesome. Okay. Well, I'd love to thank Devis again for both a really great presentation, but also a really engaging discussion. I'm super excited to see where both of these projects go, and as you sort of navigate that translation to kind of like a system that's deployed and used. And also thanks to everyone else for attending this webinar. The next webinar will be on November 22nd, and it'll be a presentation on something completely different, looking at battery and energy optimization. And if you'd like more information about climate change AI, again, you can visit the website at climatechange.ai. So thanks so much, everyone, and we'll see you next time. And thank you, Devis. It's great to see you.
Thank you, everybody. Thank you so much for being here.